So the first talk of the selected talks will be by Dr. Matteo Antuono. So, and it's entitled as the delta-LES-SPH scheme generalization to a quasi-Lagrangian model. So I would like to welcome Dr. Matteo Antuono to kindly start his presentation.
Thank you very much, Abbas, and good morning to everybody. The present talk, which I'm going to show you, is deals on a generalization of a previous model made by our group, that is Salvatore Marrone, Andrea, Mascio, Andrea, Colagrossi, on a consistent inclusion of large eddy simulation models inside the SPH framework. Specifically, our first work is Mascio et al. 2017, where we just defined the theoretical framework and we did some initial simulation up to moderate Reynolds number. The problem is that when we moved towards high Reynolds number, like for example 1 million, which are typical Reynolds number for LES simulation in other schemes, we encountered a number of problems, which I'm going to show you. The part of this presentation is first to show which are the problem, and then to describe the new model which I'm going to define. Incidentally, I recall that we are also going to do some comparison with the existing models in the SPH literature, specifically the model of Damien and Roger, which is one of the first attempts to include the LES modeling inside the SPH framework. Well, for what about the model of Mascio et al., this has been defined by using a Lagrangian filter, here denoted by the letter phi, and applying this filter to the Navier-Stokes equation for compressible and barotropic flows. In this case, the filtered quantities are indicated by the tilde symbol, and it is possible after some computation to obtain this system here, in which we have basically the same operators, differential operator, or the standard or the SPH models, and then we have some additional terms inside the continuity equation, specifically the term C1 and C2, and some additional terms inside the momentum equation, that is the terms M1 and M2. For what concerns C1 and M1, these are the filtering terms, that is, they account for the differences between the filtered and unfiltered differential operators. Is it possible to show that, however, these are very small and can be neglected? For what concerns the remaining terms, these come back from the LES approach, and specifically the term M2 in the momentum equation has been modeled following a standard approach which goes back to the work of Yoshizawa, while for what concerns the term C2, which is a new term and just arises in the SPH framework, this has been modeled through the diffusive model of Molteni and Colagrossi. What is very important to stress, however, is that if we neglect completely the term C2, we obtain back the model Darling and Rogers. Well, here's just some details about the modeling, the discretization of these terms. For what concerns the term M2, we just use a standard coefficient from the LES literature, specifically going back to Yoshizawa and Smagorinsky, while for the term C2, we defined a sort of diffusive turbulent viscosity, which is denoted by nu delta, and which contains a dimensionless coefficient C delta, which is set equal to 1.5 to obtain back an order of magnitude which is comparable with the diffusive term of Molteni and Colagrossi. The first simulation we are considering are about free decay turbulence in 2 dimensions. In this case, we started with a two-periodic bidimensional box and with a fluid at still condition. And we put the fluid into motion by using a forcing term, which is here described by these 2 formulas, which has been obtained by using the analytical solution by Taylor. This analytical solution allows us to generate a pattern of vortex structure inside the fluid domain, and this forcing term is multiplied by a ramp, which goes to 0 after t equal to 1. So what happens? For example, we can see the kinetic energy on the left figure. We have an initial increase of kinetic energy when this forcing term is acting, is different from 0. And then for t greater than 1, we have the forcing term is 0, and we have the freely decaying of turbulence. Conversely, on the right figure, we see the typical vortex pattern induced by the forcing term. In this specific simulation, we are considering Reynolds equal to 1 million and about 1,400,000 particles. Well, these are the results if we just apply directly without any additional tool these models, that is the Mascio et al. And the Damien model, to this case. As you can see, we have the onset of the so-called tensile instability, which lead to the generation of large void regions inside the domain and leads to the complete destruction of the solution. A standard solution for this problem SPH is to include a pressure background. In this case, in fact, we are able to obtain back a good simulation both for the pressure on the right and for the vorticity on the left. However, the problem is that if we compare the density energy spectrum with the theoretical findings, which predicts two different behaviors, a minus to the 5/3 law and a -3 law, we observe a sort of deviation of the density energy spectrum predicted by the model of Mascio et al. At wavelengths which are comparable with the kernel radius. And the same is observed by using the model of Darwin parameters. This is because we are using actually the pressure background. And this pressure background induces some kind of sort of a particle resettlement at wavelength close to the kernel radius. This resettlement has its own content of energy, which is observed in this strange bump profile of the density energy spectrum. So to solve this problem and obtain a density energy spectrum which is in good agreement with the theoretical findings, we first tried to remove the tensile instability, the pressure background, but at the same time we had also to remove the tensile instability. And for this reason, we used a tensile instability control term like that described in Sun et al. In 2019. In this case, this tensile instability control term relies on the use of a switch inside the pressure gradient, which goes from a plus formulation, that is Pj plus Pi, when the pressure is positive, to a minus formulation, Pj minus Pi, when the pressure Pi is negative. Applying this tensile stability control without pressure background, we obtain, however, bad simulations, especially for the pressure field, and also in a minor way on the vorticity field. And this is because even if we have no more the occurrence of the tensile instability, we still have a very noisy and disordered particle distribution, especially in those regions which are characterized by negative pressure. So in this case, we add just one last possibility, that is to add a term which regularizes the particle distribution. In this case, we tried to include in the model the particle shifting technique. Unfortunately, this is not possible inside the old model of the Mascio et al., and we had to redefine a new model in order to include the PST in a reliable and consistent way. Well, the approach is basically the same of that shown for the Mascio et al. We again have a filter, but in this case, the filter is not Lagrangian, but is quasi-Lagrangian, because we added a small velocity deviation in comparison to the Lagrangian velocity. In this case, again, we can apply this filter to the Navier-Stokes equation, we can integrate all over the free domain, and at the end we obtain this system in which we see that we have some additional terms, which are C3 in the continuity equation and M3 in the momentum equation. Like for the previous model, C1 and M1 are negligible. Differently from the model of Mascio, the term C2 is modeled through the diffusive term of the delta-SPH model, and this is because this is a 4-ordered operator, and then is expected to work more efficiently at the shorter length. And finally, we have all the other terms which depends on the addition of these small deviations, which, however, if are small, can lead to the neglection of the term C3 and M3, and we have just this term remaining, which can be modeled using the standard SPH differential operator, as in this case, as you can see in this discrete modeling of the continuous equation. In our case, we just model the velocity deviation through the particle shifting technique proposed by Sun et al. In 2019. So, this was the first simulation with the new model, always at Reynolds equal to 1 million. As you can see, we recover a good distribution for the pressure field, but again, the vorticity field shows some problems inside the core structure, which are characterized by negative pressure. And this is because the particle shifting alone is not enough to counterbalance the action of the tensile instability. So our final choice, which is possible in the new model, was to add together the particle shifting technique and the tensile instability control term. And these are finally the simulation we obtain, in which we have a good pressure field and a good vorticity field. What is important is that, differently from the model of Ditache et al., in which we observe this strange bump profile, in the new model, in the quasi-Lagrangian delta-LES-SPH model, we observe a good match with both the theoretically rate of decay, the -2, the 3 low, and the -3 low. Here I just show you a snapshot, detail of the kinetic energy of both the model. On the left, the Mascio et al. Model, on the right, the quasi-Lagrangian model. And as you can see, the new model is completely free from this short length noise, which affect the solution of the Mascio et al. Well, here I just show you some snapshot of the evolution for these cases. The animation are available at this YouTube channel of our SPH group at the link below. Well, these are the first instance in which we have the forcing term which is acting and generating the vortex structure. Then, when the simulation goes on and the forcing term is 0, we have the onset of instability, and then the subsequent generation of vorticity with the generation of a big vortex structure as predicted by the theory in 2 dimensions. What is interesting to observe is the density spectrum related to this instance that I just showed you. And as you can see, in the first instance in which we have the forcing term which is acting, we have a peak which corresponds to the wavelength of the forcing term. And then we have the resettlement of the wave spectrum towards the correct theoretical behavior. Well, after the simulation in 2 dimensions, we moved to 3 dimensions. Again, we studied the freely decaying turbulence. In this case, we use the same approach, that is fluid at rest with a forcing term acting in the first second of the evolution. But in this case, we used the analytical solution that I found in this work, Antuono 2020, on the journal Fluid Mechanics, which is an extension of the Taylor solution to a 3-periodic box. In this case, the pressure field is obtained as a function of the kinetic energy, while these are the expression for the solution of the velocity components. Actually, we have 2 different components, which are denoted by the subscript 1 and 2, depending on the fact that the solution may have a positive or negative helicity. I recall you that the helicity is the dot product between the velocity and the vorticity field. But however, for the sake of the simulation, you can choose one or the other. The solution is practically the same. Here we see a snapshot of this analytic solution, in which we have a complex 3D pattern of vortexes whose stagnation points, that is the center of the vortex, are inside these strange Y-shaped structures. However, all the details of this test case are available on the SPH workshop website, and the test case is the 16th one. Well, when we study this three-dimensional simulation, we also compared with a finite volume model, an Eulerian finite volume. As you can see, since these models are really different, we have on one end a quasi-Lagrangian SPH model, on the other end an Eulerian finite volume model. The transient evolution for the kinetic energy is quite different between these models. So for the comparison, we just choose different time instance, but however with the same amount of kinetic energy. And these are the comparison for the energy spectrum. As you can see, both the model agree with the theoretical rate of decay, which in 3 dimensions is just -5 to the third, and they also agree well one with the other. Here there's a snapshot of the evolution for the vorticity field. On the left, we can see the present model, on the right, the finite volume model. And here, the same for the contours of the vorticity field, which are qualitatively quite similar. Just a final example before ending my talk, which is somehow more practical application. In this case, we are studying a fluid which is put into motion inside a wind reservoir. In this case, this is inside a rectangular tank, and is subjected to a strong vertical acceleration, up to 10 times the gravity acceleration, as you can see in the bottom right panel. The Reynolds number here is 200,000, and we use up to 500,000 particles. And this is a snapshot of the three-dimensional domain. And here there are some snapshots of the evolution. As you can see, on the left we have the free surface evolution, and on the right we have the isocontours of the current structure, which has been obtained by using the Q criterion. And as you can see, just in the few initial periods of evolution, we have an incredible generation of vortex structures inside the domain because exactly of this strong forcing term in the vertical direction. What is for us very good is that both the three-dimensional model and the two-dimensional model predicts results which are in fairly good agreement with the experimental measurement. However, for all the details on this simulation, you may follow the presentation by my colleague Salvatore Marrone, which will be given at the SPH workshop of this year. And for the animation, I again address you to the YouTube channel of our group at this link below. Well, for what concerns future works, we are still trying and finding non-turbulent problems to test our model, and we hope soon, I don't know when, but soon, to start studying a Wolf function for this delta-LES-SPH model. Thank you for your attention.
Yes, thank you very much, Matteo. So before we start the Q&A, in fact, so I would like to once again welcome Professor Joe Monaghan, who kindly joined us and who kindly accepted our invitation to join this workshop today. So now we have about 5 minutes for Q&A to Dr. Matteo Antuono. So please, so this, we can welcome maybe 2 or 3 questions. Yes, Max, please.
So can you hear me?
Yes.
Just checking.
Yeah.
Okay, perfect. Thank you very much for the very interesting talk. I could imagine that this delta-LES-SPH will be important, or will be very important in future. So out of interest regarding your 2D test case you were looking at, so how did you validate your results? Have you checked how the entropy within the box is scaling in time, or how did you check whether it's valid what you observe in general? I mean, so far I understood you were looking after to reduce the noise on the small scale, but so when we did this kind of investigation, we always looked also on the entropy scaling in time, because this seems to be characteristic in 2D turbulence. Can you elaborate on that, please?
Actually, we had two different problems. One was to solve this strange deviation of our model, and then obtain back a good behavior. But in this case, we just look at the density energy spectrum. Actually, we didn't follow the evolution of the Einstein field. We just look to this theoretical behavior, the -5^3 law and the -3 law for the density energy spectrum.
Okay, thanks. May I ask a short other question as well?
Yes, please.
Yes.
Thanks. So regarding your personal opinion, so I really want to hear your personal opinion on this. So I think from an engineering point of view, so this tensile instability control, we sacrifice a little bit of conservation, right, for accuracy. So how do you think about that? Because I mean, in engineering, so I have the feeling that finite volume schemes are used instead of finite element exactly because of this.
Okay, then actually I spent a lot of years saying that the conservation properties of SPH are really, really important. Obviously, when you have to face really strong problems and applications, sometimes it's better to have a really stable and strong scheme. In this case, what we try to address is that you can use a model which is not strictly conservative like the standard SPH, in this case by adding the tensile instability control term, but you need also something which regularizes your particle distribution, because this avoids the generation of noise and the degradation of the solution because of bad interpolation, of bad representation of the SPH operators. Then you have these two different tools which together can help you to have a good simulation and to obtain a strong tool and a robust scheme.
Thank you very much.
Yes, thank you very much. So do we have any questions? Maybe one more. Yes, Angelo, please.
Hi, can you hear me?
Yes.
Yeah.
Okay. Hi, Matteo. Great presentation. Thank you very much. Just a question about the particle shifting. Exactly how do you apply it? Like in the sense, do you have any criterion to shift in determinate area of the domains and perhaps, you know, keep the shifting off where, for example, the structures are becoming very small and you don't want to destroy them? Like, do you do that adaptively or like, are you doing that flatly, and how do you tune your shifting? Like, how do you decide like shifting coefficients and things like that to keep the flow turbulence?
Well, in this simulation for turbulence, we have all a two-dimensional and three-dimensional periodic box. Then we just applied the shifting straightforwardly without any, let's say, turn on, turn off procedure. We just followed for the tuning of the parameters the work of Sun et al. And actually, we didn't have any problem. Probably if we have to do simulation with an important action of walls, we have obviously to rethink about the use of these terms, but in that case, we should also think about something close to the walls, like wall function, for example. It's a totally different way of modeling, let's say.
Okay, thank you.
Yes, thank you very much, Dr. Matteo Antuono. So I think we can welcome the speaker of the second selected talk, so Professor David Touzé from Ecole Centrale Nantes. And the title of Professor Touzé's presentation is Accurate Modeling of FSI Problems at Different Reynolds Numbers, Current SPH Capabilities and Limitations. So Professor Touzé, the session is yours.
Thank you. Can you see my screen?
Yes.
Okay. So, hello everyone. I will present you a work we did with Peng and Sun and colleagues in Nantes and in China, in Harbin, and now Peng is at Sun Yat-sen. It was when he was postdoc in my group. So on FSI problems at different Reynolds numbers. And I will try to highlight, since it's the topic of the session, I will try to highlight a bit what we intend with the different Reynolds numbers. So my talk will be outlined like this. I will speak a bit of the Reynolds numbers range. I will describe the model and error results, and in the end, I will have some discussion regarding the current capabilities and limitations for high Reynolds flows. So in the present simulations, the ones you will show next, I highlighted there where we are in the Reynolds number range. So you see in 2D we will have fully resolved simulation from 100 to 100,000 Reynolds number, and in 3D we have laminar situations and high Reynolds, quite high Reynolds number situation, but where we will discard viscous effects. So in reality, it's an infinite Reynolds number simulation. So bear this in mind, and you will see this pink code on every slide I have highlighted, whether it's 2D and 3D and what is the Reynolds number. So the delta-LES-SPH model, so it was already presented quite extensively by Matteo and a bit by Andrea. So I won't stay very long there. It's the weakly compressible SPH model with artificial viscosity and the delta term in the continuity equation. And in addition, this is delta-SPH. And in addition, there is this particle shifting technique with this form of shifting displacement, which was used in this work, which has the effect of regularizing the particles during the particle distribution during the simulation. There were some discussion on the consistency of such a technique. At the next FERIC, we will have quite an extended discussion of this topic of the consistency of particle shifting. But at least in terms of displacement, it is consistent, and that convergence, it has no effect. When you have a free surface, since the free surface has a kinematic boundary condition you should respect, the idea is not to shift particles there, and we have a specific treatment where in a close by region from the free surface, particles are shifted only tangentially, and at the free surface they are not shifted at all. So using this delta-LES-SPH, Peynan and colleagues from Italy acknowledged that tensile instability was much reduced compared to the standard delta-SPH. So the use of particle shifting helped preventing tensile instability. But unfortunately, it's not valid for all cases. And here you have cases where delta-LES-SPH fails to correctly predict the attached flow. So Peynan and colleagues introduced this tensile instability control Matteo described already, with this idea that if you rewrite the Pi plus Pj version of the gradient we use for conservation with an objective of conservation, if you rewrite like this, with this more accurate form, we have this 2pi gradient which is acting, and if the pressure is positive, then it acts as shifting, as a regularizing force. But if P is negative, it acts on the opposite way, and it tends to create these voids we could state here on the top part of the profile. So to avoid this possibility is to get rid of this term. Of course, this has an impact on conservation a bit, as just stated. And we do this only when the pressure is negative, and also when we are not close to the free surface. Otherwise, we know that the formulation Pj minus Pi is violating the free surface condition in some way, in an integral way, and we have free surface instability otherwise. So we use this tensile instability control in the simulation, and using both particle shifting and tensile instability, you go from there to here. If you just use this tensile instability control, but no particle shifting, you have the flow keeps attached in this simulation, but you see you have some noise in the pressure field and in the vortices, etc. So we really need those. And as I said, the examples I was showing here are around 1000 Reynolds number. We can go to higher Reynolds number. Here it's varied between 5,000 to 100,000, even more. And we have nice results. Of course, you need a high resolution to get this. If you compare to a finite volume solution of the same flow, so this is a flow past an ACA profile under a free surface, you can see that we get quite similar results. And interestingly, the magnitude of our vortices are well preserved even in the far wake with this high resolution that was used. Okay, so this is for the delta-LES-SPH model, which was past work compared to this work where I will discuss FSI, and with flows up to 100,000 in 2D. The next element ingredient we need is particle refinement. If we want to do complex flows, so what we use is the adaptive particle refinement we proposed here in Nantes. And you see that if now you're not, we don't just look at the shape of the flow, its global feature and pattern, but we want to converge in this, on this simple example at only Reynolds 2000. If we want to converge on the drag coefficient, we need up to L over delta X equal to 800 to converge to the target value. So this is a quite huge resolution on this quite low Reynolds number in 2D. And of course, APR here is important to reach this objective. And with this APR, you can get more details of the flow at higher Reynolds numbers, and Danilo and Andrea showed even much higher Reynolds numbers. But I guess a quite accurate description of the boundary layer there, even at Reynolds number in the range of 10,000, even more, up to 100,000 maybe. But in the range of 10,000, we are okay with APR and this delta-LES-SPH model with tensile instability control. Now I will jump to the structure model. So when you want to do FSI in SPH, I mean with an SPH fluid solver, you have two possibilities. Either you say you will do a full FSI SPH solver as is proposed here. It's not the only work. We are not the only ones to do so. This has the advantage that you have a unique simulation framework and you have the control of the properties. It's the same code, etc. The other strategy is to use a coupled SPH finite element FSI solver, which of course has not the same advantages. The main advantage it has is that it permits to get rid of the drastic CFL limitation due to the sound speed in the structure, sound speed with which you cannot trick contrary to fluids for constitutive reasons, which yield for stiff structures to very, very high sound speed, and very, very small time steps. So this is, for instance, the strategy we developed here in Nantes also in the past, or in the past and now. And the other advantage of using a FI, of course, is to benefit from a huge experience regarding structural modeling with finite elements. But here we don't have this strategy. We have the first strategy. And so we need a structural SPH solver. So we use the total Lagrangian structure solver as proposed by Belichko and colleagues, where we will have in the momentum equation the different stress tensor in chain. So we need the different stress tensor, strain tensor, and in the end, the deformation tensor and the gradient tensor, to which we give these SPH forms, where we use a first order correction to get these two displacement and deformation tensors. So this has been implemented. It is well known that when you do this this kind of SPH structural model, there is another kind of instability, a hourglass kind of instability which can appear. You can get rid of this with artificial viscosity or with some specific control or using stress points and projections, etc. Here we use an artificial viscosity. And we tested this structure. So this is simply an elastic plate which is hinged to a rigid cylinder, and it's free to move due to gravity in the void. And it is compared to the result by Turek and Haran. So we now have this validated structural solver, and I can go to FSI. So to couple these two SPH and SPH structure and SPH fluid solvers, since we don't have the same time steps, or at least it's clever to don't have the same time steps, what we use is a CSS coupling algorithm with multiple time steps, sub-time steps in the structure, as sketched on the right part of the slide. And we will test this FSI solver on different test cases. So most of these results were published in this recent paper in Ocean Engineering. So we first took the test cases, the famous test cases by Turek and Haran. FSI 1, FSI 2, and FSI 3. FSI 3 is more challenging because the density ratio is 1, the speed is a bit higher, and the Young modulus also is a bit higher. And we get we will use these test cases to validate. Before these validations, what we did is to do a hydrostatic test case, which is always not so easy. And the flow past a rigid body to check the accuracy of the solver before we activate the fluid structure interaction. We here a convergence plot and a comparison with finite elements results of Turek and Haran with errors on the force of the order of 1%. And so these are the results for the FSI2 and FSI3 test cases. So again, here you see that the Reynolds number is really moderate, quite low, but the flow structure is already quite complex. And if we look at the details for FSI2, we compare to their results of Turek and Haran. We compare to LBM result as well. And for FSI3, we compared to LBM simulations we did also in my group. And we have a good agreement on the different test cases. And we proposed an FSI4 test case with the presence of a free surface, which, so it's quite complex because due to the oscillations of the elastic plate, you have areas of low pressure which interact with the flow which is deflected. So you have different sources of pressure variations along the profile, and the flow and the structural deformations are quite complex even at this low Reynolds number. So maybe this test case can be used by others in the future. What we also, then we went to 3D. So one of the nice test cases in 3D is the ones developed by UPC by UPM in Madrid, sorry, UPC in Madrid, where you have oil and an elastic beam in a rotating sloshing tank. So we made comparisons. So here, if you do a 2D modeling, we showed with my PhD students in the past that there is a 3D boundary layer effect. You have a boundary layer along the two boundaries of the tank, which is very important. And if you do a 2D or 3D simulation, you get different results, and you are not able to be close to the target. So here we clearly see this boundary layer effect. And actually, the 3D result is much closer to the experimental one than the 2D one. So here again, we are at a Reynolds number of 1000, but in 3D this time. And then we did a much higher Reynolds number, which depends how it's defined. But if it's defined with the water depth, it's around 400,000. But in this case, we made the assumption that we could get rid of the viscosity, assumes viscous effects are negligible. So in reality, we don't simulate this Reynolds number, we simulate an infinite Reynolds number. And we compare to experiments by Liao et al. We compare the beam deflection, the flow, and you see we have quite a nice agreement on this test case. And what was highlighted again, that viscous stresses are not very important because we are able to compare well with the experiment. But tensile instability control is important because we have, otherwise we have negative pressure, and you see we have unphysical flow separation which appears. So the last test case I will show is quite complex in terms of flow patterns. So it's an elastic beam that is hinged to the bottom and quite flexible in a stream. So we use, you see, adaptive particle refinement quite a lot. And you have deflections in 2D, but also in 3D. It's not a full 2D deformation of the plate. We compare to results from the literature and the experimental one. And you see that in terms of vortical structures induced by the problem, it's quite complex. And we compare this also with LBM, and it's in quite good agreement. So again, this is 3D and Reynolds 1600. So regarding these results, so what we can say is that we have a quite accurate and versatile FSI model in the end, and you see both in 2D and 3D for low Reynolds number, for infinite Reynolds number, like this dam break problem with an elastic gate. So we are quite happy with the results. Now, if I go back to this slide, so this is where we were in this presentation. But if I look at and it's in my presentation, but in the whole workshop today, it's more or less the case. We have fully resolved viscous flows at Reynolds number between, say, 100 and 100,000 in 2D, and Reynolds fully resolved results at Reynolds number between 100 and 2,000 in 3D. Okay, or high Reynolds flows, very high Reynolds, where viscosity is negligible because we have impact or fast dynamics kind of flows. But in the main use of current mesh-based CFD solvers, like car industry, pumps, turbines, ships, planes, etc., the range of Reynolds number is not this at all. It is this, but this with important turbulent effects. So not the possibility to get rid of the viscosity. And so we are not there, okay, in SPH. We are there, but we are not there. So it's what I wanted to discuss a bit in a CMAM paper in 2011 we did with my Italian colleagues. We investigated the boundary layer only at Reynolds 10,000 in 2D, and you see that we had needed already very fine particle size compared to finite volume to be able to capture the complex boundary layer. And this is 2D, Reynolds 10,000. So if we want to go to 3D, like on a ship, the boundary layer at the end of a ship is already only a few tenths of centimeters for a 300-meter long ship, for instance. This is not enough, and APR is not enough. why our current API is not enough? Because you see what are the meshes used in finite volume method. They are extremely non-isotropic. You have aspect ratio up to 1000 close to the wall. Even if we target a Y plus of roughly 30, we will still have an aspect ratio of 30, 50, etc. And with our current APR, we do refinement, but it's isotropic. Okay, we refine in all the directions in the same way. So this would be very too costly. So I guess we need a wall function, as Damien said. We need hybrid RANS and LES as it's currently done in mesh-based method. So we see that we are on a good track with LES. The past talk of Matteo, in the past there were RANS model, etc. But Damien talked largely of it. So we need those ingredients, and also we need a non-isotropic APR. So for me, it's all this work we have to do if we want to be able to play in this playground. Of course, this may not be a target, but if we want to have SPH which becomes really more large and versatile in terms of applications and maybe competitive, this should be a target. And of course, a target with fast efficiency in terms of CPU or GPU implementation, which is always a challenge. So this is what I wanted to highlight. The last track we started to investigate with the Italian colleagues is to say, okay, we restrict SPH where it's needed, so only at the free surface to describe complex free surface, and we try to use mesh-based method otherwise, so you can do some coupling between here finite volumes and SPH. Again, this was only a proof of concept with a quite moderate Reynolds number, but in 3D. But this may be actually a great option for SPH as well, instead of trying to redo what finite volumes are currently doing. Okay, so that's what I wanted to say. Thanks for your attention.
Yes, thank you so much indeed, Professor David Touzé. So I think we have about 4 or 5 minutes for Q&A, for questions and discussions, please. You can just use the raise hand option or just type your question in the chat section as well. Yes, please. Mr. Hai Ching, please.
Hi, Professor David. Hopefully you can hear me.
Yeah.
Regarding your FSI simulation, may I know, do you employ any turbulence models to ensure the stability at high Reynolds number?
No, as I said, the high Reynolds number case, which was displayed, so the only one is this one, and it's inviscid, okay? I mean, this is a physical Reynolds number, but the simulation is inviscid. The Reynolds number is infinite.
Okay, thank you.
So there is no turbulence model at all. But as you see in this kind of results, and this was said already in this kind of flows, this was said already by Damien, in this kind of flows, it's perfectly legitimate to get rid of viscosity. For impact flows, it's mainly driven by inertia. So the pressure is driven by inertia. And of course, if we want to go to other kind of high Reynolds flows, like flows past an object or a profile object, as I mentioned, there it's another story. You have turbulence which is originated from the boundary, and it's another story. Because what I didn't, maybe I was a bit quick, but there are two kinds of turbulence. You have ambient turbulence, like in river flows, atmospheric flows, etc. And you have turbulence which is originated from the boundary. And in the large majority of industrial applications, turbulence is originated from the boundary. So you need an accurate boundary layer at high Reynolds to be able to describe these flows. It's not the same, it's quite different, but this is the vast majority. And you have cases where turbulence can be neglected, and this is only a few cases, impact flows, gravity waves, etc., which are currently addressed by SPH.
Okay, thank you, Professor David.
Yes, thank you. So do we have any questions, any other comments? Yeah, I think this part is very important, and of course we can consider it in the panel discussion that we have today. And also Professor Damien Violeau also mentioned about this, in fact, for consideration of the wall functions and also paying attention to the accuracy, and also turbulence will be of secondary effects, but depending on where we are in terms of Reynolds number, and if we are like doing some industrial simulations applications, as yes, this slide here. So I think we can have one more question, final question. So if you have, please just, yes, please, Professor Leon.
If turbulence is not properly resolved, why there are differences between 2D and 3-dimensional simulations? Because some of the problems in your last 3 or 2 applications are purely 2-dimensional.
So in what I showed, the 2D problems were fully resolved. So they were either laminar or transitional, but they were DNS if you want. So if there is turbulence, or it's, I don't know where you define turbulence exactly and how you define it, where it starts, but it was fully resolved for the 2D cases, like even the, I guess the highest Reynolds number case showed was not FSI, it was there. Where was it? Sorry, I lost it here. Okay, so I guess this is fully resolved. Okay, so no turbulence model, DNS. In 3D, I just displayed laminar test cases. So of course there is even no turbulence physically. Laminar test cases, and the only non-laminar test case I displayed was this test case where turbulence is obviously there, but it has a negligible effect on the problem because it is an impact problem.
Okay, so in this simulation, the 2D, 3D, FSI, SPH, so they produce roughly the same results.
Yeah.
But I remember some of the simulations, the 2D, 3D results are a bit different.
Yeah, okay. They are, in this example, they are different because this is much more viscous. And what happens on the walls, the boundary layer along the walls, along the 2 side walls of the tank, this boundary layer induces a 3D effect. Okay,
yeah,
this
so
is not turbulence. This is a laminar situation.
Yeah, thanks.
Thank you. I think there's one question in the chat section. Hi, Professor, is your APR solution adaptive?
Is it adaptive? It's more and more adaptive now. In this simulation, it was not much adaptive. In what we do, it's more and more adaptive, but it's not as adaptive as what we have in finite volumes where, or finite elements where it really, for instance, follows vorticity, contours, etc. Very closely, but we are going towards adaptivity, yes. For now, it moves with with the body, for instance, and also it can change shape a bit, but it's not as adaptive as AMR in a standard CFD solver or standard or advanced CFD solver.
Okay, yes, thank you very much. So thank you very much, Professor David Touzé, for your impressive presentation. And I would like to invite the last presenter of today's talks, so Mr. Max Okraschevski, please. So he will talk about implicit molecular stresses in SPH. Max, please.
Right, thank you. I will share my screen. So I'm working. No. So can you see the presentation now?
Now we see, yes.
Okay, perfect. Then, yeah, thank you for having me here today. This is a really great opportunity to present our theory about implicit molecular stress in SPH. So the aim for me for today's session is to give you a new physical explanation for these particle bottlenecks we normally observe here at high wave number in the turbulent kinetic energy spectra obtained with SPH in a DNS sense when considering turbulence. But before I dive into the topic, let me introduce myself. I guess I'm quite unknown. So you see me in the upper right. My name is Matteo Okraschevski. Since 2018, I'm a doctoral candidate / researcher at the Institute of Thermal Turbomachinery in Karlsruhe, Germany. And from an engineering perspective, we are actually interested in kerosene atomization in aero engines because we want to mitigate emissions. And therefore, our group leader, Dr. Rainer Koch, you see him here left from Monaghan actually. This is a photo taken at one of the earlier conferences, had the idea to develop or tackle this problem with weakly compressible SPH in order to gain new insights into the process. So in the development of our own in-house C++ code, which is actually massively parallelized, was achieved by mainly these three co-workers you see here, especially the right one focused on MPI parallelization. And I think we were quite successful with that, as you can see from the left video. So this is from one of our biggest simulations comprising 1.2 billion particles. So this is a virtual reality animation. Basically, you see me very small in the upper right corner again. And as you can see, we were able to reproduce characteristic structures of the atomization process quite well. For example, as you can see here, this back breakup, which is well known from the experiments. So when I started at ITS, there was one central remaining question for us, namely, can we capture SPH or can we capture turbulence with our classical conservative SPH at finite resolution? And I think nowadays the answer is quite well known. So SPH really struggles with that due to different mathematical issues, which are mainly missing zero order consistency. So I just want to shortly recap what this is. So basically it means if we try to approximate an arbitrary function or its spatial derivative, then we will end up with remaining terms which can be interpreted in SPH on a very high level as noise. And the effect of this noise can be quite severe for the simulation results, and especially for turbulence. This was very well presented by two German guys, I think, as well, Bauer and Springe, already in 2012. So this is what you see on the right-hand side. So they simulated subsonic turbulence, which was steady in average sense, with smooth particle hydrodynamics, as well as moving or mesh-based methods. And the outcome is what you see here. So in orange, these are the entropy fields, or in other words, the local rotational energy of the turbulence. And as you can see, whereas the grid-based methods reproduce the characteristic fine structures quite well, SPH really struggles with that and suffers from massive oversmoothing, at least for this classical SPH variance, which is the cause of the noise. So this is what we know already. So SPH suffers from excessive numerical dissipation. And what I now want to do is to ask whether we can physically reinterpret this mathematical issues, or may there be either other conceptual physical problems with SPH which are not governed by mathematics. So and why should we do that? We should do that because SPH is very physical from the beginning. Normally when we derive SPH as a methodology, then we use the Hamiltonian or Lagrangian of the overall particle set within a top-down approach, and obtain then approximation of the mathematical operators. So when we do so and ask this question, then we will quickly realize that SPH is not fully Lagrangian at finite resolution, but behaves pseudo-Lagrangian. And this term was already introduced by Vogelsberger in 2012. So what does pseudo-Lagrangian mean? So it means basically, if we focus, for example, on the particle trajectory, which I tried to visualize here on the right-hand side, then this is indicated by this dashed line actually, then in average, and this is the best case, we can follow the true Lagrangian trajectory, but we see normally we have this perturbation, and this is introduced by the noise already mentioned on the last slide. The other thing is that we completely neglect deformation kinematics, and this is not described by the mathematical issues on the last slide. So here what I mean is basically that if we expose the particle or the spherical kernel to an arbitrary flow field, then it will not adapt locally to the actual fluid flow. And this is something we cannot consider with SPH. So, and this is basically what motivated our work. So we wanted to quantify this pseudo-Lagrangian behavior with SPH. And therefore, I would like to draw the attention to the following. Namely, we can reinterpret SPH from a molecular dynamics perspective. Why is that the case? Basically, we have two strong arguments for that. So as we have seen already on the last slide, particles are bad representative of fluid elements anyway, so they behave pseudo-Lagrangian. The thing is now, if we assume that one particle is governed by Navier-Stokes, this is what I try to indicate here, then we implicitly assume that one particle equals one homogeneous fluid element, actually. And we know from experience that this is not always successful. The second argument is that we are already using molecular dynamics native estimates at certain stages in our code. For example, and this is well known and often utilized, the volume approximation. It is basically depending on a local spatial average over particles, molecules defined by the kernel support. And what I thus want to propose is actually, why don't we just use the kernel itself as a better representative of a fluid element, introducing the concept of so-called kernel-based fluid elements, because on the kernel scale, we can measure noise, we can measure deformation, and even better, we can consistently reconstruct the Navier-Stokes equations with molecular dynamic arguments, namely the Hardy theory. And this is what we did in our work. So we focused on isothermal flows and obtained the so-called kernel transport equations, which actually describe the dynamics of one kernel fluid element, as you can see in the upper right corner again. And this is what I tried to summarize on this slide. So let's dive into this model. So as you can see, for the mass transfer, we have the very common density approximation, also molecular dynamics native, actually. But if we now apply Hardy theory, then we end up in a natural definition of the kernel velocity here highlighted in red. And this is the velocity with which one kernel fluid element is transported. If we dive into the definition, you see this is nothing else again as a local average over the SPH particle velocities. And the consequence of this kernel velocity is quite severe, because it means in general that even for the center particle, the difference between the center particle velocity as well as the kernel velocity will be generally non-zero, meaning there is already the similarity to ALE schemes, and we call this relative velocity, which are introduced due to this kernel velocity concept, peculiar velocities. And they are actually fundamental for our theory. So this is what you see again in the momentum transport equation, which is actually the focus of the remaining presentation. So this is what I summarized here. On the left-hand side, you see the force acting on the kernel fluid element. This is connected to the actual particle forces, which you see here on the right-hand side, represented by the acceleration, and they are connected to each other by two different processes. The first one, well known from SPH itself, which is low-pass filtering, we see here in the second term. In the first term, we see a new stress term emerging, and this stress term is basically depending on the tensor quantity, which we call the molecular stress tensor. And again, here we see this similarity to ALE. So what is our goal? So our goal is still to find a measure for pseudo-Lagrangian behavior. And that's the reason why I want to convince you that this molecular stress tensor, which is actually depending quadratically on the introduced peculiar velocities, is such a measure. Why is that the case? So we just dive into the definition itself. And as we can see, this is again a quadratic form in the peculiar velocities. That means for sure we will measure velocity noise and velocity differences on the kernel scale. Why that? So imagine this kernel fluid element here again exposed to this linear shear flow. What will happen is for sure that the SPH particles will adapt to the velocity profile, but in a noisy way, meaning that this is quite obvious. More interesting is now how the resulting forces are acting. And therefore, I would like to consider the following example. So this is a 1D nozzle flow, very intense. We are not focusing on boundary layers here. And if we now introduce a spherical kernel element here, which we call KT1, and track it in a Lagrangian manner, then it should be stretched due to the acceleration. Why is that the case? So let's dive into the profiles we have assumed. So as you can see, the velocity profile has a non-zero curvature, and as a consequence, the forces acting on the left and right boundary of K will be unequal, resulting in stretching. Contrary to that, the molecular stress tensor counteracts the actual Lagrangian deformation. How can we see that? This is what we can see by linearization of the peculiar velocities. If the kernel fluid element is sufficiently small, then we see that the peculiar velocities here are a function of the gradient of the velocity profile itself. And if we now plug it into the definition of the molecular stress tensor and evaluate its divergence, then we will see that the resulting emerging force here is actually a function of the second order derivatives of the velocity field. In other words, the Laplacian, meaning it will introduce diffusion, which actually counteracts the Lagrangian deformation. So and this is what we were after looking for, basically, to pin down to the Lagrangian behavior locally. This is, in that sense, very good news. So when we now apply the molecular stress tensor to a real SPH data set, as we did on the next slide, then we can learn even more interesting things. So and therefore we considered a turbulent flow field. Why turbulence? So as already explained, the molecular forces are a function of the curvature of the velocity field. And we know that in turbulence, we have a lot of wrinkling, a lot of folding, meaning there's likely a lot of velocity field curvature. And what we did here was to simulate with one of our weakly compressible SPH variants, the experiment based on the work of Rivera and Wu. So we were focusing on weakly forced 2D turbulent flow under the assumption that the particles are twice as fine as the measured Kolmogorov scale. And what we find is basically that we can reproduce the flow. For example, here on the left-hand side, you see the evolution of the vorticity field. After a while, we reach a steady state in average. So this is what we wanted to see. And even quantitatively, if we look at the Eulerian kinetic energy spectra, then you see that the dots coming from the SPH solution are following the slopes of the inverse and the direct cascade quite well. So the thing is now we were only able to reproduce the flow with the dissipation, which is actually 2.8 times higher than the measured dissipation from the experiment in terms of entropy. And also we observed this particle bottleneck here at high wave number, which is well known in literature to be also linked to the kernel scale. So what I now want to do is to ask whether can we explain this effect by the molecular stress concept if we apply it as a post-processing indicator. Indeed, we can. So therefore, we applied an eigendecomposition of the molecular stress tensor for one certain snapshot, and we can compare it to the vorticity field. So this is what we do here. As you see in the first row, you see for one snapshot the vorticity field. It's just reproduced in the second column for visual purposes. And in the second row, you see the eigenvalues. The first eigenvalue here, the second eigenvalue, they have the same color bar, same magnitude. And if we now compare high vorticity areas to the eigenvalues, you see that there is a certain link between these quantities. For example, here this vortex core, this blue vortex core here, has a high magnitude in the first and second eigenvalue. You also see that this characteristic high vorticity patches here are linked also to high values in the second eigenvalue of the molecular stress tensor. So what can we conclude from that? So we know that SPH, and this is just empirical observation, basically, that SPH struggles with vortex dynamics at finite resolution. We also see that the molecular stress tensors, or the molecular stress tensor has high values in its eigenvalues, linked to high vorticity areas. And the molecular stress tensor is itself emerging from the kernel-based fluid concept, so it's related to the kernel itself. And this link could explain that SPH suffers from implicit molecular stresses in case of vortex dynamics. So I think this could be really, really helpful in order to improve SPH in general for these kind of problems. Even more interesting is now that not only we have this link between high vorticity and implicit molecular stress, but also that the molecular stress is organizing itself in a characteristic spatial structure. And this is what we can see if we look onto the eigenvector corresponding to the second eigenvalue, because this was the most dominant one, as we could see from the last slide. And if we now dive into this black highlighted region here, so in the middle of the snapshot, and now superimpose the velocity field here as a vector field and the second eigenstress as a vector field. Now again focus on this vortex core here circled by this blue color. Then you see by comparison that the velocity field and the second eigenstress are dominantly oriented perpendicular to each other. So this is quite interesting. So what could this possibly explain? So therefore I would like to abstract this vortex core here as a generic vortex model. So the easiest one is the Gresham-Chan vortex. So we know that SPH normally to excessively diffuse this vortex in radial direction in the tangential velocity component. And what we now presume at this stage is that these molecular stretch modes, so exactly what we observe here, could be the physical explanation for that, because the molecular forces redistribute energy from the tangential to the radial velocity component. And this is, I think, very valuable insight and definitely deserves attention in the future, I think. So that's what I wanted to share with you for sure today. I think this is only the tip of the iceberg. So I think, especially for theorists, this could be really valuable because what we can see from the kernel transport equations is not only that low pass filtering is eliminated in formal convergence limit, which we consider here, but also that we eliminate this new molecular stress tensor term here, which emerges from our molecular dynamics concept. And furthermore, and this is what I already mentioned besides, so there is some similarity to ALE. Maybe it could be valuable or interesting also to find a unified theory for that. And finally, I would like to conclude with the following. So for the practitioners, especially, how can we use this theory now to improve current SPH? So therefore, we have recommended two research paths in our paper. One of them we already started to explore, and hopefully you will read from us very soon. So what we did here is to explicitly consider now the molecular forces in our SPH simulations, focusing on Taylor-Green flows for higher Reynolds numbers. This is what you see again here on the left-hand side. You see the vorticity field develops nicely into 2D decaying turbulence. And what is now important is that if we focus on the kinetic energy evolution on the right-hand side, then you see by comparison of the solid to the dashed lines representing the cases where the molecular forces are explicitly considered, that we can mitigate numerical dissipation. And why? This is what we want to explain in our new paper. And in that sense, I would like to thank you for your attention. Hopefully there's some very interesting questions in order to start a fruitful discussion. And yeah, thank you again.
Yes, thank you very much, Max, for your interesting presentation. So I think we have about 6 or 7 minutes for questions and discussions, please. So there is a question in the chat from Professor Andrea Colagrossi. So please also consider for your future works past literature. So there is a paper by Elero et al. Implicit atomistic viscosities in SPH, Physical Review 2010.
Yeah, thanks for this remark. We considered this, we cited the work of them for sure. So I think this is this also motivated our work actually. So we think that they used the formalism of Irving and Kirkwood to consider for the investigations, and I think we just generalized their theory. So without their idea, our work wouldn't be possible. So we are well aware of that. Thank you.
Okay, yes, thank you very much. So do we have any other questions, comments to Mr. Max Okraschevski? Yeah, just before we welcome another question, so maybe I can just remind the scientific committee members about the Google form, please. So do we have any other questions for Mr. Max? So can you start thinking about comparing SPH and PIV?
So just to get the question correctly, so meaning PIV as a experimental method, so particle image velocimetry?
Particle image velocimetry.
Yes, that's correct.
Okay. So Spontaneously, I can't say.
It's a spontaneous
how...
question, so indeed, a spontaneous answer is welcome.
Spontaneously, I can't see how our theory could help with this, but yeah,
what I mean is
it.
with PAV, but possibly it's not even correct. The PAV is not even the correct term, but and here I failed. Anyhow, what okay, I reformulate the question another way. You're making an investigation at SPH, looking really at the formation of very small volumes. As I saw it, as I understood it, but this is also something that you can get from experimental techniques that concentrate on very small volumes as well, and especially visualization. So you get information about the rate deformation, strainer rate deformation, these quantities also from experimental data. Now you are kind of mimicking these kind of processes, looking at the almost looking at the kernel as a voxel in a way. That was the intuition behind my spontaneous question. So I was thinking, is it really possible now that we kind of begin to match the high resolution SPH with high resolution experimental techniques that really look into small volumes, very small volumes of fluid? I don't know if it makes sense, but it's just an idea.
It could be. Thank you. So it could be a really nice idea. Maybe I think we certainly or for sure have to involve the experimentalists. So I'm not so my knowledge is not that big in this area. So in that sense, I think the idea is very well, and we have some colleagues here working on PIV. So I will definitely start a discussion with them. In that sense, yeah, thank you for this remark, but that's everything I can say.
Yes, Professor David Touzé, please.
Hello, thank you very much for the presentation. I was thinking in what people do in finite volumes to correct this this I don't remember, you called it pseudo-Lagrangian. I don't remember exactly the wording, but the fact that we don't deform particles as we should, because actually they are deformed by the flow, and we always keep them as a circular particle or spherical particle. What people do in finite volumes is that they are doing AED, is that they are actually correcting with the shape of the element, which is able to evolve, like the work of Sashkov and others, for instance. So they have extra operations of corrections and corrections of the fluxes due to this effect. But there they have nothing more. So I was wondering how your theory, and they still have Navier-Stokes. So I was wondering how your theory matches this kind of corrected AED, or whether it is totally different. I don't know if I'm very clear.
That's a really interesting.
It's compensated in finite volumes in a simple geometrical and associated fluxes way. Okay, and this is still full Navier-Stokes at macroscopic scale. And you are on another track, and I was wondering whether these two tracks they are the same. I mean, formally they should give the same results.
So this is a really interesting question. So and this was also discussed in the work of Vogelsberger, who introduced this term pseudo-Lagrangian behavior. In their work, they were comparing moving mesh methods with SPH. So he was from the same group as Bauer and Springe, and they actually had this idea as well. And what they were concluding was basically that their mesh method is or has already this features which you have described right now. So, and they were saying or referring to that as quasi-Lagrangian. So as in the talks before mine. And they were saying, since they already have a tool which can capture this kind of behavior, they were not interested to improve their SPH method in this direction. So this is what they say directly in the conclusion of the paper. But yeah, it could be actually the link you mentioned right now. So maybe the stress tensor could help to go into this quasi-Lagrangian direction again. And I think there's also again justification also for the delta-LES-SPH scheme, because there we also have these additional stress term, and Boussinesque modeling is also very similar, motivated as this molecular stress tensor itself. So I think there are a lot of important things we can learn from this kind of view. Yeah, definitely.
Yep.
Okay, so thank you very much. So I think now it's time for starting the panel discussion, which will be chaired by Professor Benedict Rogers. So once again, thank you very much, Mr. Max Okraschevski. So I will welcome Professor Benedict Rogers to kindly start the panel discussion.
Yes, thank you, Abbas. I'll just start sharing my screen. One second. Okay, so hello, everybody. My name is Ben Rogers, and it's my pleasure to be chairing the panel discussion session for this SPH Online workshop. And this morning, we've heard quite a lot of very interesting talks from different areas of turbulence in SPH. And so this sort of panel discussion is trying to sort of maybe sort of delve into some of these issues a bit more deeply. And we've got some very eminent people on our panel, and some people who are making brand new entries into the world of turbulence in SPH and shaking things up, which is always good. So we've got Professor Frederic Diaz, Professor Damien Violeau, whom you've heard from already this morning with their talks in the first session. We also have Dr. Massoud Rezavand from the Technical University of Munich, who's a researcher there. We have Dr. George Fourtakas from the University of Manchester, who's a lecturer in complex flows. And then we have Jackie Tsurudomi, who's a researcher now working in Criepi in Japan, and has recently obtained her PhD in SPH from the University of Cambridge. So this sort of panel discussion is trying to look at some of the issues that people have been talking about today. I've been saying this morning because it's my morning, but actually I should just say today. In particular, we want to sort of talk a bit about sort of turbulence and boundary layers, and we've heard quite a bit about that today. So the format of what this panel will take is that we're going to have a few sort of short overviews from each of the panel members for about 2 to 3 minutes. And before this panel, we tried to pose some sort of key core questions. And then we've got some other questions as well that we might get into if we have time. And so then we'll come back to all of this at the end. And so just to remind people what these questions are, okay, so these were our core questions that we put to the panel and also sent out to all the delegates of the workshop. So first one is, what are the challenges to developing robust turbulence treatment in SPH and resolving boundary layers? Could we identify new grand challenges for turbulence or boundary layer flow in SPH? Where or under what kind of conditions is turbulence modeling, or will turbulence modeling be crucial in SPH simulations? How should we decide upon the selection or the incorporation of those turbulence models in SPH? What kind of theoretical numerical considerations should be taken into account to better reproduce the boundary layers in SPH? And quite importantly, people mentioned this a few times this morning, what kind of benchmark tests are needed for rigorous validation of turbulence and boundary layers in SPH? And then this one always crops up, how can we improve the accuracy of turbulence modeling near a solid wall boundary? So those are the sort of the core questions that we'd like to sort of try and consider if we can this morning. We don't have long, we've only got about sort of 20 minutes or so. So I'm going to go through the panel members in turn. So I'll start off with Professor Diaz, and I'll move on to Professor Violeau, then Massoud and George, and then Chiaki at the end. So I'm going to ask each of the panel members just to speak for 2 to 3 minutes on their sort of opinion on these core questions, or maybe what we've heard so far. So first of all, I'll start off with Professor Diaz.
Hello. So thank you. Well, I'm going to be brief because, you know, there are definitely more experts. But as I mentioned earlier, I think, you know, the benchmarks are really important. So, you know, for me, you know, the core question 6, what kind of benchmark tests need to be considered for rigorous validations of turbulence boundary layers in the context of SPH? I think in terms of wave breaking, there is definitely, you know, the possibility to develop some benchmark tests. I'm not so sure about the boundary layer aspect of things, but, you know, for the turbulence, definitely with wave breaking. The other question, and it's more, you know, asking a question is, for example, the point 7, how to improve the accuracy of turbulence modeling near a solid wall boundary. We all know that it's already, you know, very complex with the other types of methods. So what are the additional complications with SPH? So that would be the second point. So yeah, and then, you know, could we identify new grand challenges for turbulence in SPH? So again, you know, and this is because it's my area of research. I think, well, first, you know, for wave breaking, you know, definitely the modeling of wave breaking with SPH is an important challenge. And also, you know, there are so many different models of turbulence. So which one, you know, is the most appropriate for SPH? So these are just some rough ideas, but I will stop here.
Okay, thank you, Professor Diaz. Now I'll ask Professor Violeau to give his opinion on these questions.
Thank you, Ben. I would say that about the second question, that turbulence and boundary layers in SPH is a grand challenge. Now, the question 3, I guess, is fundamental, and I briefly addressed it in my presentation. So as I said, it's an open question, and I guess that it depends on what you're looking for. For example, if you're modeling waves, as I said, apparently turbulence is not crucial while modeling propagation of waves in a channel. And I would say that it's even better not to have a turbulence model than to have a bad turbulence model. If you're using the K-epsilon model for wave propagation, for example, you're going to see your waves damping too much. On the other hand, as Frederic said, if you're looking at wave breaking, of course, turbulence plays a crucial role. And as well, if you're interested in the velocity profile near the bottom of the channel. Next, and to finish this first contribution to this panel, I would like to address briefly, excuse me, let me read again the questions. Yes, benchmark test cases. I guess that the question of the distribution of turbulent quantities, including average velocities in a steady flow on a straight plane wall, is very important. That so-called log layer is quite hard to model. We succeeded in modeling it with a Rance approach, but not with an LES approach. And I guess that any attempt to progress in turbulence modeling in SPH should consider this case as a basic case. It's also important in that case, or even in the case of a slowly, gently curved surface, to check how SPH can predict the Reynolds stresses, especially for fluid structure interactions.
Okay, thank you, Damien. So already we can see some sort of emerging themes coming out of people's opinions, which is interesting. So next, I'm going to ask Massoud to give his opinion. Massoud's come from a different perspective, I believe, not quite so focused on the free surface hydraulics that both Damien and Frederic specialize in. Massoud?
Yeah, thank you very much for the introduction and the organizing here, you and Professor Fenger. To me, it basically looks like that we need more, in a nutshell to say, is more theoretical work on SPH, on turbulence models in SPH. I think this is quite kind of missing, and in order to have a clear picture of how we could model turbulence effects in SPH, that's kind of some direction that one has to work. So this is basically the question on number 3. Then, because the other questions were highlighted by the other members very nice and clearly, and I would focus on this one because we already know that SPH is quite powerful for free surfaces and so on. And the point is that if we really need say direct modeling of turbulence, or we could ignore that. And another point is the wall modeling in our team and our applications that we are working on. Well, we are focusing on industrial flows recently, and for some applications like slug flows and so on. So we need to clearly address the effects of the wall boundary conditions, and that's some sort of the things that was also highlighted for today's workshop in the nice presentation of Professor Violeau in particular. And we saw that it's first very important to also take into account the effects of solid boundaries, and that's one of the points that I would also draw the attention to. Thank you.
Thank you, Massoud. Yeah, very, very interesting. Wall modeling is a clear point, and more theoretical work. I'm going to come back to you on that to see if we can identify exactly what needs to be done. Next, I'm going to ask my colleague, Dr. George Fourtakas, to give his opinion on these core questions.
Thank you, Ben. Thank you very much. Hello, everyone. So I think the talks today is summarized very, very well what is missing or what we need in SPH. And there were 3 specific questions that were coming up or discussion. One was accuracy and stability, which so happens to be Grand Challenge 1. The second one was boundary conditions, which so happens to be Grand Challenge 2, and adaptivity, which, if I'm not mistaken, is Grand Challenge 3. So as a Grand Challenge, turbulence modeling exists in the spheric grand challenges, and we need to resolve all the other 3 in order to get to millions and millions of Reynolds number. So at early stages of SPH in the 90s and 80s, I think turbulence was not possible or was out of the question in my opinion, but obviously now with all the new developments, this is in the horizons. Now, for me personally, the biggest problem is the source of error we have in SPH, and that comes from particle anisotropy. And what my colleagues in Manchester have done is they went a step back and they're looking SPH from an area perspective. They do that so they can have a very accurate discretization scheme based on SPH. and very accurate boundary conditions, the second, fourth, or whatever order you want. So that is, I think, a step we might need to consider as a community, how accurate is our scheme and how accurate are boundary conditions. Now, early results show that we can model separation quite accurately and viscous flows. I think Damien's talk summarized everything quite well from Meran's LES perspective. Since we cannot model all scales, we need to use some sort of modeling, either RANS or LES. For very small eddies, obviously, you need to model things and you need to apply some sort of particle refinement in specific areas, obviously, to model as much of those eddies as you can from an LES perspective. We have the choice of either resolving the boundary layer, which again, adaptive resolution is very, very important there, or using a log law. And again, for very high Reynolds number, even if you are using a log law, you need adaptive resolution as well. So what you're gonna resolve or what you're not gonna resolve depends on your modeling scheme. So you can look at the Taylor scales or look at the Kosmolov scales, or be very brave and have millions and billions of particles and go for a DNS for high Reynolds number. I think this summarizes what I want to say in all. Thank you, Ben.
Okay, thank you very much, George. Very interesting, some good points there about some of the intrinsic nature of the SPH method itself. And finally, I'm going to ask Chiaki Tsuradome to talk about these core questions.
Right, thanks. Can you hear me?
Yes, we can.
Okay, so I did completed the PhD work recently, and not a specialist in turbulence modeling, but in my understanding, so there are many challenges recognized so far in terms of the turbulence modeling and bound layers. One of the biggest challenges is the instability problem, pressure instability, tensor instability, and also particle disorder and the errors in conservation of momentum as well. But the talks today showed a very good achievement performance, and also shows good suggestions for future work, right? So personally, I think that what the existing other methods can do should be done in SPH, of course. And besides that, we should achieve only SPH and the particle method can do in turbulence modeling. So, so as for question 2, could we identify new challenges? Yes, we can, but I read the reference papers about grand challenges, and actually it states that the SPH working group and the grand challenges do not cover all the matters, all the fields that should be researched in SPH. But the target issues are general and must be addressed to compete with the existing models, right? So in that case, for me, turbulence modeling and boundary layers problem are not a single challenge, but a complex challenges related to all other grand challenges 1 to 5. So that's my personal opinion.
Okay, thank you very much, Chiaki. Yeah, I think you have summarized that very nicely at the end by saying it's actually a complex combination of many of the other issues that we face in SPH. I just want to come back to Massoud. Before we move to the audience, I just want to discuss a couple of points raised by the panel. Massoud, you raised a very interesting point, and I want to sort of play it off against what Damien presented earlier, when you said that we need more theoretical work and that's missing. Could you sort of elaborate on what you mean there?
Yeah, sure. The point is that, at least for today's presentations and the talks and also in the literature, I personally can't find a clear picture and a comparison between the classical turbulence models. As we know that, okay, we are not capturing such large Reynolds numbers, so it's not basically maybe like a real turbulence model, but the concept of turbulence closure, as we saw, for example, again in the presentation of Professor Violeau, we see, okay, we have RANS or LES or a couple of other numerical and turbulence models. So we do have this turbulence closure, and we do need just to include some extra stress tensors into our governing equations, but this was something that I couldn't capture during the theoretical works, which ended to simulations. And this is for me something that has to be elaborated on in the community.
I mean, did the other panels agree with that? I mean, Damien presented this morning the Langevin model, the LES model, the RANS model. Do people agree with what Massoud has just sort of highlighted? George, your hand is up.
Well, I think Damien, and I'm talking on behalf of Damien, apologies, Damien, but my take on Damien's presentation is that the RANS and LES models, finite differences, finite volumes have been using for the past, I don't know how many decades, can be applied to SPH. However, you have to be careful on your discretization scheme. Is a discretization scheme that creates the particle stability, the problems in the pressures, etc. that Antuono was discussing. Is not the turbulence models. That's my understanding. So if you have a scheme, an SPH scheme which is accurate enough and stable enough, then you shouldn't have any problems with the closure models.
Damien, I'm wondering if you could sort of respond to those two comments. Damien, can you hear us?
Yes. Well, I agree with what George said. To summarize, you can apply any of the existing models for turbulence in CFD to SPH, provided you have a good scheme, especially near the wall. As for the Massoud's idea that more theory is necessary, I think, Massoud, you mean that more theory about the fact that SPH is Lagrangian?
Yeah.
And there is a very interesting discussion of that in the paper that goes together with the presentation by INSEAD, Matteo Antuono's presentation. And again, as I said at the end of my presentation, I have the feeling that their model may be one of the key solutions for turbulence in SPH as soon as it is applied to boundary layers. Checking that the log law can be reproduced in average with this model would be very interesting.
Yes, I mean, something that nobody mentioned today was that if you look at people who have been working in turbulence for decades, in fact, in other methods, they actually get quite concerned about the higher order moments, but they look at the velocity fluctuations. And nobody mentioned this today, and it's something that I think could be quite both interesting and challenging in SPH. As far as I'm aware, nobody's looked at this. Do any of the panel have any other experience on this, or any other opinions on the importance of the higher order moments for the fluctuations that are discussed within normal turbulence models.
Yes, Ben.
Yeah.
If I remember well, one of your first presentations to Spheric was investigating the numerical Reynolds stresses in SPH in a pipe due to the Lagrangian nature of SPH. You remember that?
I do, yes.
And in fact, well, it was, I think it's more or less in what Massoud said, and also in what one of today's speakers said, Mr. Okraschevski. The idea that the Lagrangian nature of SPH induces additional stresses. And in fact, without any mention to SPH, the fact that the true fluids should be considered as Lagrangian is very important for turbulence. And the alpha model of turbulence that I mentioned and that was applied to SPH by Joe Monahan as under the name of SPH epsilon model is based on the Lagrangian averaging. There is a deep physical consideration behind this. So this is also what I said that it would deserve more attention.
Mm. I agree. So I think that sort of that nicely links up Massoud's point and various other points. I'm just going to try and bring in some points that were raised by members of the audience. So Min Luo said, this is his comment, so one intrinsic feature of real fluid turbulence is the fluctuation of fluid quantities like position, velocity and pressure. Particle methods, if not using enhancement schemes like particle shifting and diffusive terms, are subject to spurious fluctuations of fluid quantities, the magnitude of which may dominate, I think, the real turbulence associated fluctuations and hence are difficult to reproduce. Particle methods using the enhancement schemes produce smooth results, but the real turbulence associated fluctuations may also be smoothed out. So one of the challenges is to simulate the real turbulence associated fluctuations. That's kind of coming back to what you were talking about, Massoud. Am I right? And also what Damien was mentioning literally
yes,
just.
Yes, and again, please read Joe's paper, the 2010 paper on the SPH epsilon model, and then you can go to the referred paper of Navier-Stokes alpha model of turbulence, who was originated by Foyas, Holm, and others.
Yes, okay. And
but you can use the intrinsic SPH fluctuations of particles and take advantage of these within the X-SPH variant to make some natural, it's more numerical than natural, but to make these fluctuations useful to model true turbulence.
I think so. I think there has to be quite a strong link to some of the stuff we were beginning to touch on in the last talk, and also the work of Marco Alero and Pep Español. I think there are some interesting links between all of those different areas, but there's no coherent, in my experience, there's no coherent sort of theory linking them all. They're all quite sort of interesting areas of discussion.
It might be, if you allow me, it might be interesting in one of the future regular spheric workshops to invite an invited speaker who would be a specialist of turbulence for regular CFD, to present, for example, some theoretical developments on Lagrangian averaging in turbulence. And by the way, you have some colleagues who could do that, maybe Tim Kraft.
Yes, yes. We did have somebody from Ecoftac come and talk to us about sort of the CFD implementations of some of these Eulerian turbulence models, but I suspect someone a bit more theoretical would introduce some nice discussion. Okay, I'm going to move on to the next question, which came through, which was from Yuma Shimizu. This is actually a topic that's come up quite a lot today. When boundary layer is involved, even for grid particle scale, we should need a sufficiently refined resolution. And since the very fine resolution for all a computational domain is not possible due to the limitations of, it could be CPU, it could be GPU, or an MPI accelerated code, then the problem of the boundary layer is linked to adaptivity. And you saw the presentation by Professor Touzé earlier, who was looking at this. On the other hand, multi-resolution SPH cannot provide the same accuracy as the single resolution at this stage to the best of its knowledge. That's correct. That is developing very enhanced dynamic particle refinement or coarsening. Does anyone have an opinion on this? Massoud, do you have an opinion on this at all?
Finally. Again, very important, as expected, as highlighted in many talks today, could be one of the solutions. And we are also interested into this for adaptive resolutions close to the boundary layer and close to the wall. And also, as also mentioned here by Yuma, of course, then comes the issue of computational efficiency. One has to capture the small eddies and get really fine resolutions close to the ball. And that also comes again with other grand challenges as well, like the efficiency and so on. Very important.
Yes, as Chiaki mentioned, all of these, in actual fact, to take on turbulence correctly, as Chiaki said, all of these grand challenges actually come in together, which is also a point made by George.
Exactly.
Okay, I'm just going to move on to the next question. So, I wonder if I could bring in Professor Diaz here, seeing as we spoke about benchmarks. The comment by Yuma was, since one of the biggest advantages of SPH is easy handling of free surfaces, the benchmark test case for turbulence, which includes free surface boundary conditions and has rigorous theoretical solutions, is best. You're coming at this from a slightly different perspective because you are looking quite often at extreme waves and fluid structure interaction. Suggesting benchmark test cases, that's quite fraught with difficulty. Have you sort of changed your opinion at all listening to all of the talks today?
Well, I mean, the developing benchmarks has never been easy, and and as you know, we developed this benchmark for ISOP, and it was definitely a challenge. And then it was not only SPH, it was all types of methods. Because it's difficult doesn't mean that we shouldn't do it. The benchmark we developed for ISOP was something theoretical because we couldn't do the experiment. So I think it's definitely useful to have a benchmark coming from an experimental campaign. What we just did is a nice combination because it has breaking waves, it has a moving body because of the impact. So there is the interesting question of the friction with the bottom. So how you make an object move. So I think the experiments is. Well, the first campaign was made, a second campaign will be made. So when we make the second campaign, we can keep in mind, what could be useful. The thing is, we don't have theoretical solutions. So, that's the other challenge. But I think a carefully thought benchmark will be useful.
Yeah, it's essential. In fact, I mean, Matteo Antuono presented, one of the few sort of theoretical cases for things like the three-dimensional vortices, but that solution obviously doesn't go to very high Reynolds numbers, and that's a problem that we have. I mean, we can steal the benchmark test cases that are used by the normal turbulence community. But with SPH, we have to demonstrate that we can do the test cases of the other models and then other ones which show off the advantage of SPH as well. So actually it's doubly difficult for SPH to do this. Damien, you have your hand up.
Yes, I would like to say that according to me, if you consider the Reynolds averaged framework, there is no known theoretical solution of, say, the K epsilon equations, for example, even without a free surface. And with a free surface, it's even more difficult because nobody knows what really are the boundary conditions of the K epsilon model at the free surface. This is because the free surface is a highly anisotropic turbulence area, as spotted by Andrea Colagrossi.
Yeah,
this is a difficult question, but this is of no importance for our applications, I guess, because the dynamic of turbulence at the free surface in general is not important unless you have a breaking. It's for wave breaking and splash up that turbulence is important. But having a rigorous theoretical solution in this case, I think it's hopeless.
It's very difficult, but I mean, Professor Diaz, at the beginning, you mentioned about wave breaking being a good test case for turbulence in SPH, but of course, wave breaking is inherently multi-phase, and that's an extraordinarily difficult problem at that point. And we sort of we end up coming back to statistical measures of the energy decay within a broken wave and that sort of thing. And that I'm not sure whether that would it's a very challenging application, but I'm not sure whether that would be helpful, as it were, for the incremental development of the turbulence modeling within SPH at the moment.
Yes, I'm not so sure. As you mentioned, the multi-phase aspect is definitely, a key aspect of this wave breaking. So, well, that's maybe for 20 years ahead of us.
Yeah. Okay. Well said. Okay, there were just a couple of other comments or questions that came through just for the panel. So, in fact, Pengnan Sun earlier, he said, is there any benchmark test for turbulence modeling of multi-phase flows? My guess is that there is for very constrained cases. Can any of the panel answer that question for Pengnan? So that's this second one here.
It depends on what is called multi-phase flows.
Exactly. Yeah, exactly. It depends what is a multi-phase flow. So the wave breaking case, that's actually depending upon the surface that the wave is breaking, that can be a three-phase problem. Okay, Ming here asked this quite a good question. It seems that SPH is inherently good at simulating turbulent phenomena comparing with grid-based methods. That's possibly arguable at the moment. Therefore, should the criterion for selecting or incorporating turbulence models in SPH be different with the criterion and grid-based methods? And can we roughly establish a criterion or a list of some situations about what condition should the turbulence model be used in context? Jackie, I'm wondering whether we could bring you in here, because I think you were looking at solitary waves in your PhD, is that right?
That's right, solitary wave propagation over porous structures.
And so, I mean, with your background in porous flows, I mean,
yes.
how would you choose, for example, the choice of a turbulence model between either grid or a particle-based simulation technique?
For me, honestly, I had no choice but to use the SPH subparticle scale model. Then unfortunately, I didn't find much significant difference with and without the turbulence model. So in fact, the turbulence of a porous flow is very crucial in coastal engineering. So I wanted to see the turbulence, but the problem is that the SPH model I used is the very original one, so not the new brand new. So now the SPH model should be improved a lot, then it should be successful. But at that time, I failed in modeling the turbulence, and also because I implemented the porous structure modeling, probably some resistance force or turbulence effects are included in the additional resistance forces due to the porous structures. So when we consider which turbulence modeling and also boundary layers treatment, then we have to take consideration in what we will see in simulations, and also what other like coupling methods or techniques we use. Then it might be compete with the turbulence model we will choose.
Yeah, in fact, I mean, the reason I brought you in there was because I know you've done porous media flow, and that's a topic that nobody's actually touched upon today, and turbulence within that sort of application area. And so these decisions about which model to use become very, very difficult, especially when we have people saying, well, the theory is not correct, or we still need to do a lot of work. So I think we probably got to the end of the time that has been allocated for this panel discussion. Before I draw it to a close, is there any member of the panel who'd like to say anything or any last comments?
Yes, please.
Yes, George.
Yeah, sorry, Ben. Just on the comment of Pegnan on the benchmarks for turbulence modeling and turbulence modeling on multi-phase flows. So there are a lot of DNS libraries that look at these specific problems, even for multi-phase flows. You can have heated surface with bubbles raising up. And there are DNS libraries that provide such data for us to use and validate our models. Obviously, free surface, as the panel member said, is quite a difficult matter. But before we jump to free surface, maybe we should look at the classical DNS libraries databases and compare against those.
Yes, I think this is a point actually that Antonio is making in the chat when he's talking about regarding benchmarks for turbulence and free surface flows. There seems to be an issue to define what DNS is, but we can certainly make use of what they're doing there. I think I'm going to finish actually just by quoting what Professor David Touzé has written in the chat. He says, a large part of the past and current turbulence research aims at understanding it and producing models. There are thus two different possible paths forward for SPH, taking advantage of the particle framework, so it's conservation of the discrete properties, to have its own SPH path and modeling, and secondly, to make possible SPH simulations with existing turbulence modeling for problems where SPH already has advantages. So I think those are things to think about. We've run out of time, unfortunately. So at this point, I'd like to thank all of the members of the panel and also the very excellent presentations this morning. I'd just like to say thank you very much to Abbas for organizing this excellent workshop. So thank you very much.
Thank you so much, Ben. I think the panel discussion was absolutely impressive and, in fact, fruitful for, in fact, especially young researchers for working in the field of SPH, because you shed light on the state of the art of turbulence modeling and also, in fact, inspiring the young researchers for rigorous research in this regard. So I should apologize that we are behind about 20-25 minutes behind the schedule, but we had very impressive talks, impressive discussions. And so for concluding remarks, I would like to welcome Professor Peter Stansby for kindly delivering the concluding remarks of this workshop. Professor Peter Stansby, please.
Okay, hello everybody. Can you hear me okay?
Yes, perfect.
Yeah, good. Well, first, we must congratulate Abbas for organizing this meeting with 5 excellent talks, in fact, actually 6 excellent talks, which have been quite challenging. A lot of what I was going to say has actually been covered quite well, really, by the panel discussion and also by the speakers. So I'll just emphasize a few points and be as brief as possible. I mean, what is quite clear is that SPH has come a long way in the last 10 years, and Andrea Colagrossi called it the age of darkness 10, 15 years ago, and maybe we're now in the age of enlightenment, helped a little bit by the fact that we've got GPUs enabling a lot of the new ideas that are being developed. I mean, just looking back a little bit very briefly, I mean, the original sort of problem 10 or more years ago was that with weakly compressible SPH, the pressures were actually very noisy, and this was clearly not very good. And then incompressible SPH came along, which removed the noise, and with particle regularization or shifting, this produced really quite accurate solutions. And then weakly compressible SPH sort of rose to the challenge with delta SPH, and then mixing that with particle shifting to produce very, very satisfactory results, many of which you've seen today. And we've also now as well as got PST or particle shifting techniques. We've got TIC or tensile instability control. So really things have become from a basic sort of numerical point of view, really we've done a lot, and to, you know, you can use these methods really with some confidence now. Another sort of issue some years ago was actually representation of the solid boundary, and mirror particles were very popular, but now we've got various options of various levels of sophistication, and we can actually get to high order in representing solid boundaries now, and certainly first order is sort of should be standard. So this is all, you know, made the method you know, much more, gives us much more confidence. On the question of turbulence, which is what the subject of this workshop is about, I mean, we've had a very good discussion actually on what we're actually doing here, but in the first eddy viscosity or Kepler model was used, I think probably about 15 years ago by Damien, Violeau and Issa, and not that much has been done along those lines since, but there's been a lot of work done on LES, which fits naturally with SPH, and the talk of Matteo Antuono showed some very impressive results, and clearly, you know, there's going to be lots of progress as LES is refined and SPH is refined. It does seem as though as the accuracy and the order of solutions with LES increases, the potential for LES increases. I mean, for some applications, and not where SPH is perhaps not being used, but in combustion, for example, the standard numerical simulation is actually 6th order accurate. So you do need very high accuracy, and for that sort of problem, actually Lagrangian methods would be highly beneficial. Also interesting to see from Matteo Antuono's presentation that he's showing vorticity results, which seems to be a much better test of solution quality than pressure, which is easy enough to actually output. However, having said all that, LES is inevitably expensive, and so in terms of general purpose computations or more industrial type computations, we need sort of more conventional turbulence modeling, and turbulence modeling and its sophistication is actually a grand challenge, not just across SPH, but across the whole of CFD, and has been for many years. Damien has sort of suggested that we should try Reynolds stress transport modeling, which is a good idea, and you certainly need that for secondary and swirling flows in many applications. And I think actually, I think there are sort of well-defined experimental data on rotating flows, which would be quite sort of relevant to test these things. But as well as Reynolds stress transport modeling, where you've got 7 equations, 6 Reynolds stresses, normal and shear, and the dissipation rate, as well as Reynolds stress transport modeling, there is the option of low Reynolds number K-epsilon modeling, which is the standard actually in finite volume CFD, whether it's ANSYS or whatever. And here, perhaps we need to get a bit lower than the Y plus of 30 that David mentioned, to some maybe like 5 or 10 even, to get into the low Reynolds number K-epsilon sort of regime. And this is a standard actually in for many industrial applications using commercial CFD. And commercial CFD, is a massive industry in all sorts of areas: turbo machinery, aerospace, and so on, and of course shipping. So there's low Reynolds number K epsilon or K omega, which is a variation on it, which is popular. But there's also something that's not been mentioned actually, or maybe it was hinted at. There's also nonlinear K epsilon modeling, which we did actually try, I don't know, probably quite a long time ago, 20 years or so ago, with finite volume methods for predicting flow around the cylinder, circular cylinder, from subcritical to critical to supercritical Reynolds numbers, and it actually worked really remarkably well. This is these nonlinear K epsilon models are sort of 2nd order and 3rd order. Tim Craft in Manchester, who was mentioned, has been sort of instrumental in driving many of these, but they're pretty good at doing transitional flows, which is obviously rather important, and also at predicting separation, which is why the flow around the cylinder was actually quite well predicted. So I think, stepping back a bit from Reynolds stress transport modeling, there are sort of more sophisticated K epsilon type models which might be worth a try. And I think that there's a challenge there. It could be, clearly SPH has got a lot of advantages for many flows over mesh-based methods, free surface flows, mixing, multi-phase flows, and so on. But if it could actually be confident, we could be confident about having sort of standard low epsilon, low Reynolds number K epsilon models, then that would be sort of a major boost, which is actually being discussed about in the discussion forum just now. But finally, I don't think anyone's going to argue this is highly desirable. And in fact, all these things are highly desirable. We do need to have APR, or adaptive particle refinement, which David Touzé talked about in his talk. But it does appear to be, I think this is probably a major challenge, because as David said, you know, the resolutions you need near the boundary are really rather refined. I mean, the resolution normal to the boundary is obviously much greater than that tangential to it. So how do you handle that? I mean, some ideas are pretty obvious, but it's a question. You know, they've got to be made to work. So yeah. So I think that is this adaptive particle refinement area, which should be non-isotropic, and is very important. Maybe the big challenge. I mean, progress has been made clearly by the Nantes group, and Renato Bacondio did some early work, which was quite good. But maybe that's the next big thing. So that's all I want to say. It's been a really strong workshop, in my opinion. Presentations were excellent. Discussion was really insightful. And I look forward to the next online 3. And I say again, thanks to Abbas for sort of organizing it. And actually making sure that we were almost on time.
Yeah, sorry, because in fact, presentations were so impressive, I didn't want to stop them. And thank you indeed, Professor Peter Stansby, for your impressive, in fact, concluding remarks, and insightful and impressive indeed. So I should, before in fact closing the workshop, I would like to once again, in fact, thank everybody who joined us. And especially, so we had Professor Frederic Diaz, Professor Peter Stansby, Professor Chinwei Mao, and so many respected and eminent professors who joined us today. Yes, actually, I don't forget the prize, so please just, I was just going to express gratitude first, and then we will just, I have a presentation, so here, so continuing this presentation. So basically, very quickly stating, so we have 2 special issues. So one of them is on applied ocean research. So deadline for submission is May 10th. And Professor Panji Lin, in fact, the editor-in-chief, he was invited, he kindly accepted, but he suddenly had another meeting today, so he couldn't, unfortunately, join us. But for the European Journal of Mechanics, so the editor-in-chief, Professor Frederic Diaz, is here. And we are going to have this special issue for SPH in European Journal of Mechanics v Fluids. And submissions start from June 1st, and it will end October 1st. So we had all the guest editors here today for both special issues. I think Professor Amonjan could not join us, but he said that he was going to join if his schedule permits. So this is just for your kind information. And the other one is that we are going to have the regular, in fact, spheric workshop. So this year it's going to be virtual. And the file that I sent you today includes all this PowerPoint file, and then you can refer to the link here. And you can, in fact, we are going to have more than 60, I think maybe 64 impressive papers and impressive presentations, which is going to be on from June 8 to 11, in fact, and it's going to be organized by Dr. Angelo Tafuni. So this is also one more information. And the other information that I would like to give, in fact, is related to the Best Presentation Award, because we had, in fact, 7 committee members here. They were kindly, of course, all the grades, as you can see, are very, very close. But I would like to announce the Best Presentation Award. Congratulations to Professor Damien Violeau for obtaining this award from SPH Online II. And finally, in fact, for next SPH Online, so actually we would like to continue this beside the regular spheric workshops, because fortunately, hopefully soon we are going to have face-to-face conferences. But in addition to that, we may continue with, in fact, SPH Online, maybe once a year or twice a year, depending on your, in fact, interest. So we are going to organize this. And so based on the Google form that we have here, so August 2021 and September, they have very close, in fact, votes received here. But I did also prepare a very quick, in fact, voting. If you can just quickly consider this voting today, to maybe we can choose the date today for like August 16, September 6, or March 28, 2022. So if you have like these days, we may just consider both form, because I believe many of you, in fact, could not, access to the form, because the form, some people like mentioned that the form is not available to them in China, for instance, or other countries. But currently, we can just have a look at this poll to see what is the preference of people who kindly joined SPH Online II. So maybe in less than 20 seconds, I'm going to end the poll. So yeah, so basically based on the poll that we have here, it's like September, I think, September 6, 2021. Yes, September is gaining more votes, so I'm going to end the voting. So September has 17 votes, and March 9 and August 11. So I heard also from from the Google form, so many people told me, so August is vacation period, so it's not preferable for them. September and August are very close, but in this poll, in fact, we have September 6, 2021. So we will hopefully organize SPH Online 3, so during September, so for that specific day that we mentioned. So finally, in fact, I would like to thank all the participants one more time. So we all belong to one family, SPH family, so we collaborate for continued development of SPH. And I'm very grateful to all respected participants, all respected professors, all the panelists for very fruitful, very insightful discussions. And thank you indeed again for joining us today. Thank you.
Thank you very much, Abbas. Bye.
Thank you very much. Please take care.
Thank you, Abbas.
Yes, thank you, Ben. Thank you very much indeed.
Thank you. Bye-bye.
Thank you.